Market acceptance.
Welcome everyone to, I guess, the 11:40 talk. I'm James Lewis. Thank you very much for the invite back. I was last here, I don't know, 3 years ago, I guess, and then it's been put off and put off and put off. So thank you very much to Gregor and the organisers for inviting me back. I'm today going to be talking about this topic: team topologies, software architecture, and complexity science. But really, I'd like to give you, I guess, a brief background as to why I'm going to talk about this, why I'm interested in it. So I've been involved with computers since I was writing BASIC on an Acorn Electron when I was about 9 years old, when we used to get a computer magazine delivered once a month, and you used to copy out the code snippets to build up like a text-based adventure game. And then I started, I went to university and blah, 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 and I started programming professionally. And I think of this talk as sort of a summary, if you like, of pretty much all the things I've learned, if you like, about programming in the large. Not programming in the small, not how to structure classes and namespaces and software design in the small, if you like. But software in the large, software architecture in the large-scale organization of stuff, whether that's software itself, that's enterprise architecture, whether that's the teams that go to build that software or build that software, or the organizations in which those teams work. And as I've sort of become older and I've had more experience, I've become more interested in that. I've become more interested in the large scale. I mean, don't get me wrong, I still love writing code. I'm loving C# at the moment, especially now it's on the Mac, right? It's awesome. But I'm fascinated by the large, and I think that's possibly because I read physics at university, and specifically astrophysics, and I quite like the big concepts, how big things fit together. Science, if you like. So that's what this is about. It's about a sort of my journey as a career towards how my head is working at the moment. And I'll cover off, obviously, these topics as I go, I hope. So, if you don't know who I am, my name is James. I've worked for a company called ThoughtWorks. I've been working there nearly 17 years now. We're a software consultancy headquartered in Chicago. I work out of the London office. And we build bespoke software for people. And my mate, our chief scientist, is a guy called Martin Fowler, who you might have come across. Now, I was lucky enough back in 2013 or so to spend a week at a sleepover in Martin's house, where we together wrote what became, I guess, the sort of definition of the microservices architectural style. Back in 2014 or 2015, I'd say, has anyone heard of microservices? And people would go, no, what's that, James? I bet I'd get a different answer now, right? It's become, I guess, the predominant architectural style by which people are developing software these days. Now, for right or for wrong, I make no value judgments. You can still build monoliths if you like, that's fine. But back in the day, what we said was this. We made this statement. We cannot say there's a formal definition of the microservices architectural style. And the reason, and in fact, microservices has never appeared on the ThoughtWorks tech radar, because it's not so much a recipe as a set of characteristics, a set of properties that we were observing at the time with very large organizations and small organizations of lots of different types and domains that seemed to be making them successful. It was a bit like extreme programming, companies coming together and doing a bunch of stuff that was better practice, but doing it all together and doing it all the time. And these were the characteristics that we identified. I won't go into these in depth. But I've spent, since then, since boiling down what Netflix were doing, what the Guardian newspaper group were doing, what Tesco, who I see are represented here, the new Tesco EPOS system is based on microservices under the hood. What all these big companies are doing are adopting some of these characteristics in order to deliver software successfully at scale. But as I say, over the sort of years since, I've been thinking a bit more deeply about, are there reasons why these things work? Why is it? Not just that we observe these things and they appear to work if we use them, but why do they work? What is the reason underlying? And I think it comes down to, for me, the thing I've noticed is the theme running through is this idea of autonomy, of decoupling, of cohesion around business concerns, not technical concerns. So things like Conway's law, business capabilities, componentization, and things like pushing governance and data governance out to the teams. So putting the decision making in the hands of the people who know the most, rather than the people who know the least, which is the whole going up the chain. We have to ask the architecture review board what to do. So this is really my journey to understand why is it that decentralization, why is it that these principles of decoupling and cohesion, single responsibility and so on, have become so successful or allow us to deliver software so successfully and have led to these giant companies. But first, I want to start with I guess, the book du jour or whatever. I can't really see, but I'm going to ask the question, who's read Team Topologies in the room? Very few hands going up. Who's heard of Team Topologies in the room? Okay. Slightly more, but not that many. So I'm hoping that I'll convince you to go out and at least take a look at this book and the research in it. So Matt Skelton and Manuel Pais, who wrote Team Topologies, and it was only published a couple of years ago now. They've been long-standing members of the London Continuous Integration and DevOps communities. They've been organizing meetups, they've been listening to people, they've been working on their own software projects, obviously, for their own clients. And what they've done is take everything that they've heard about, again, what makes things successful, a bit like microservices, and put it into this book, Team Topologies. And what it does is it gives us a vocabulary to talk to each other about how to structure software teams, and therefore software systems via Conway's law. I'll come on to what those structures are in a minute. But I wanted to, first of all, give you this quote. So I'm very lucky, I'm a consultant, I get to travel around the world to places like this, but also, I go to this workshop every now and again in the Caribbean, on the Caribbean island of Anguilla. And at that workshop, there was not only Mel Conway, he was there. Mel Conway actually exists, by the way, he's a real person. He was at this workshop, I met him. But there was also someone from Amazon, specifically from AWS. And they said this: the bigger we get, the easier it becomes to get bigger. And that sort of piqued my interest, as it did many of the other people in the workshop. Because this seems to fly in the face of my experiences trying to scale organizations, trying to scale development teams. I've scaled small teams, I've scaled up to 200 person engineering organizations. Okay, it's not Accenture, but it's still, it's fairly sizable. And this is not my experience, that it becomes easier as you add more people in. My experience is the opposite. My experience is things tend to slow down, right? Communication overheads increase. The information flow overtakes our ability for the capacity we add to improve our throughput or add more value. So why is it that he said this? This person said this. What could possibly be going on at Amazon? And the thing is, he went further than this, and he said, actually at Amazon, it's not only the easier it becomes to get bigger, but the only limit on us scaling, the only limit on the number of teams we could build is how fast we can hire. We can just add more teams, more teams, more teams. They're completely decoupled from one another. They're just building products on their own, and they can just deliver value, and we just add more teams, more teams. In fact, there was a headline in the Guardian newspaper this morning that they were a bit worried about running out of people because they're going through so many people. They're hiring so many people in the US. And he said that's the limit. The limit of how fast we can go is our hiring process, how quickly we can bring teams on board and how quickly we can come up with new product ideas or features for AWS. And then he sort of went on, we were talking with Mel Conway, and he started talking about the idea of what we do at Amazon is we optimize for flow. We optimize for the flow of work. We optimize for how quickly we can get from an idea through into production, through a product actually delivering value to our users. Which brings me to this definition, which is mine. The goal, I think, of successful organizational design is to optimize the flow of value, right? All else is subordinate. And when I say good organizational design, I mean as well software architecture and design. The goal of good software design, software architecture, is to optimize the flow of value. Because one of my colleagues had the great point, it's no good having the perfect build pipeline, right? Or the perfect event-driven architecture, the perfect messaging system, right? If no one is using it, right? It's about the flow of value. It's about delivering value to people, whether that's value in a monetary form or whether that's value in the form of saving lives in medical imaging or medical hardware or whatever. So this idea of optimizing value. Daniel Terhorst North has a different way of putting it. It's that our team should be looking to safely and sustainably reduce the lead time to thank you. I like that idea. The lead time. It's not enough to get the software into someone's hands and them using it. They need to be pleased. They need to be saying thank you for the new features that they're getting. So this idea of flow, of moving stuff from idea through into production, that is the goal of the software architectures we build and also the teams that we build and the organizations we use to build that. But what is value? Let's talk about value. What is value? And in my mind, value is stuff, right? It could be any type of stuff, right? What we do in general, that value is information related, right? Someone has an idea or a customer has a want, and we take that idea, we progress it through a series of stages through our teams, and then finally it's in the hand of the customer. But it could be something else. It could be a car. It could be something physical. It could be the raw components that a customer's ordered a new Volvo, say, and the raw components are pieced together in an assembly line, and then a car turns up and they say, thank you, because I like my new car. But they're the same thing. And I think as software developers, we often think a little bit too much about just the team that we're in, as opposed to thinking systemically about the overall systems in which we work and optimizing for the overall, not just for the local. As I say, if you squint a bit, right, what we do and manufacturing is pretty much the same thing. We're just taking different types of stuff, adding value to them through a series of steps, whether that's development, followed by QA, or whether that's a BA writing user stories, a developer writing code and committing, and so on. Or whether it's a series of machines taking widgets, creating higher value widgets, creating higher value widgets. These two things, from an information perspective, if you like, are the same thing. It's basically taking raw materials of some type or another and turning it into a thing. Now, when Amazon say, the easier it becomes to get bigger, it's all about the flow of value. We get faster as we get bigger. This is an example of something called a value stream map from one of the clients I worked with some years ago. Now, when I say about the flow of value from beginning to end, this is a value stream map of a 100-plus-year-old company of how they deliver software. At the one end, you've got requirements being gathered. You've got a series of value-adding activities for some notion of value. And at the end, you've got software being deployed into production, someone saying thank you. That should scare the bejesus out of you. That's really long, right? If I point out with my laser works, this little thing here, that's writing code. That's it. That's the only code that's been written. Oh, that's the only code being written in the whole process, is that little bit there. All the rest of it, this bit here is there's two different types of data architect who've each got their own model, enterprise model, canonical model. They just go around in circles for about 4 weeks, updating each other's model. Has no effect on the process at all, apart from blocking the whole thing for 4 weeks, right? And then some code gets written, and it goes through a series of 8 weeks integration, 8 weeks regression, 8 weeks set, et cetera, performance until finally something happens in production. This is the sort of thing I see as a consultant in lots of organizations, these really, really long value streams, where everything takes an age to get done. This is depressing if you're working as part of this, right? Any code you're writing in here, it's going to take months before that sees a customer. As a developer, I want to be writing code, I want to be pushing that code into production as fast as I possibly can, and I want the users to be using that. That's what motivates me. Those endorphin hits, the same endorphin hits you get from the red-green refactor cycle, and then commit. Those little wins, little bits of value being delivered and earning us money or saving lives. But these sorts of value streams, they sort of knock the stuffing out of you. They take the breath out of the room. They make everything slow and sad and depressing. You could be infinitely fast as writing code in this process, and it would still take you 5 months to get any work done. If you were infinitely fast at writing code, that's sad. Which is why I think team topologies is such an important piece of work. Because what team topologies does is it takes the ideas of value streams, it takes the ideas from lean product development and from continuous delivery, and it gives us a set of team structures we can use to organize ourselves, to deliver software that doesn't look like that value stream. The other thing that's really nice about it is because it provides us with this language, it's almost domain-driven design-like. It's a ubiquitous language we can share, and we can use shortcuts to talk about different team structures with one another. And the other thing I like, there's more, there's lots of things I like, but one other thing I like is that it doesn't pretend there's only one answer. It doesn't say there's a silver hammer you can use, and thou must use a product team. What does a product team mean? What happens about all the other people working in ops and all the people who are working on those really complicated subsystems that we have to have? Not everyone is a quant, right? Not everyone can work building financial models. And for traders, you need specialists to do that. And often we sort of forget this, and we say, oh no, product teams have to be a product team. So what Team Topologies does as part of its model is give us these 4 different types of team structure that we can use to optimize and organize ourselves. So the first one is this idea of a stream-aligned team. Now, I talked about value streams. You wouldn't have a value stream-aligned team for that whole value stream. What they're talking about here is things like your typical sort of product teams. They call them value stream-aligned teams. So if you've got maybe an e-commerce site, that you're a retailer, you might have a stream-aligned team around your basket. You might have another one around search, another one around catalog, who are owning everything end to end, and who have, and this is the crucial bit, they have a direct line of sight to the customers of that part of the site, part of the software. Then they talk about this idea of enabling teams. Now, we all know it's really hard to get hold of certain skills. If you're hiring for InfoSec people, if you're hiring for good security engineers, hiring for good user research people, product people, these are really limited resources. So how do you enable your organization to effectively use the ones you have? Well, you put them in these enabling teams, where they act as consultants to the rest of the organization, rather than expecting to have one DevOps per team. Let's have these enabling teams. You then have these complicated subsystem teams, folk who look at things like financial modeling, or the 4 people who know how to work the mainframe, who write code for the mainframe still. That's a complicated subsystem team. And then finally, the idea of platform teams. So teams whose job it is to make all the other teams go faster. Not just running the platform, but building the tooling and providing the tooling to the other teams in the organization that allows them to get better and to go faster. And this is all about flow. It's all about organizing around the flow of value from idea. The value stream-aligned teams have a direct line of sight from the customer. They can pull their requirements through. And then you've got the other teams who are making those value stream-aligned teams go faster. So it provides us a vocabulary, and it also acknowledges the fact that there's no right answer in these things. It gives us a set of patterns we can use, if you like, to build up our software engineering organization. And I think, personally, it's one of the most important bits of work, or sort of meta-studies, if you like, about what we do that's happened in the last couple of years, along with continuous delivery some years ago and Accelerate, which I'll come on to in a second. Now, I said team topologies was one part, so is software architecture. How are these things related? Well, I've been talking about Conway's law for quite a long time. It's appeared on the ThoughtWorks radar. It's been around since like the late 50s. So Mel Conway sort of postulated that the structure of your software, the design of your software, will end up looking like the information flows between the people who built the software. This was then much later on validated in a paper called The Test of the Mirroring Hypothesis by Microsoft and MIT. It was a joint program looking at the Windows operating system. And they said, actually, yes, what we have found is the Windows operating system, the way it's modularized, looks like the teams we put together to write the Windows operating system. So what I'm saying is these things, and what we found is these things are intrinsically linked. You cannot separate the architecture, the software, the design of what you're building from the structure of the people who are building it. And if you take people out, you get different software. If I'm not there for 4 weeks, you'll get a different set, you'll get different lines of code that I would have written than someone else, if someone else is there for 4 weeks instead. And we can't get away from this. So they're intrinsically linked. Back to this quote, the bigger we get, the easier it becomes to get bigger. And I said, in my experience, this is not the case, right? In my experience, it's more like this. This is Fred Brooks, the Mythical Man Month. Adding manpower to a late software project makes it later. And again, there is lots of research done around this. You add more people, you're adding more information overhead again. More project management needs to happen, more meetings need to happen until eventually the capacity you add doesn't make any difference because the overhead is too great. You don't get additional throughput. So how is it that Amazon have managed to get to this point? Because I ran some numbers and warning, pseudo graph incoming, right, for the data people in the room. I apologize, this was the only available data. It's a log-log graph of revenue versus number of people employed by Amazon. And what this shows with this exponent here of 1.15 is that as Amazon is doubling in size, they're making more than double the revenue. You think, oh, well, that's fine. Of course they are, because it's Amazon. They're amazing, right? But this is unusual. I'll come on to why this is unusual in a moment. But the point is that Amazon are scaling faster than they should. And the revenue numbers plotted against people back that up. They're going faster than they should be going. And why is that? Well, I think it's because they've built a software architecture, both in Amazon.com and AWS, that's optimized for flow, back to this idea of team topologies. I talked about having a direct line of sight of the customer. That was one of Jeff Bezos's principles, mandates, demands, 20 years ago, nearly 20 years ago now. All teams must have a direct line of sight to the customer. But he used other forcing functions, if you like, for flow. Forcing functions that change their software architecture, change their team structures, change the way people communicated, and therefore how the software integrated that they were building to optimize for flow. You've probably heard all of these things, right? Teams must communicate via interfaces. Those interfaces must be externalizable. We're not any longer going to be talking to each other's databases underneath, right, via throttling through ETL or direct calls or whatever it is. We have to be talking through externalizable interfaces, interfaces that we must be able to turn around and sell to someone else, if you like. That's where AWS came from. AWS came from the idea of providing externalizable interfaces onto infrastructure APIs. But these are forcing functions to enable Amazon's teams to work together at a distance, right? Decoupled from one another, and to provide cohesive services as part of those teams. And this idea of two pizza teams. As I say, these are, in my mind, forcing functions for the software architecture to improve flow, limiting interaction to nearby teams, team isolation, and then scaling by this idea of Dunbar's number. So limit, smaller teams. I'm not saying it's 5 people. It might be 20 people, 15 people, whatever. And then in units of that. And by doing that, they've created this behemoth, this thing that is growing faster than, by claim, it should be. Which comes back to what I said at the start, which is why? Why are these things, this idea of decoupling, cohesion, right, flow, why are these things, decentralization, at the heart, or at the sort of bottom, if you like, of what makes what we're doing at the moment successful? And I think it's to do with this idea of complex adaptive systems and complexity science. So, strap in, there's some maths coming up. There's lots more graphs of silly things. So complex adaptive systems, they sort of arrived with us they were a gift from an organization called the Santa Fe Institute in the US. This was set up as a sort of offshoot or by a gang of ex-Los Alamos National Laboratory physicists in the main, but also other disciplines. People like Murray Gell-Mann, who was deeply involved in quark theory of matter. Right? So, they were deeply interested in this idea of how you get something as complex as a human from something as simple as a quark, right? How do you build up these things, the complexity from simplicity? So here's some interesting correlations, shall we say. What's the difference between mice and elephants? So this is a graph of metabolic rate for mammals as they double in size. Log again, right? So as you're doubling the size of a mammal, what happens to their metabolic rate, the amount of calories they need to take in as they grow. And it turns out you'd expect, as you double the size of a thing, to have to double the size, the amount of food you would take in, the calories you would take in, right? But it's not the case, actually. As you double the size of a mammal, they only need about 3/4, 75% of the calories that they should, that intuitively you think they should need just to keep those cells going, right? So you've got this variation, 75% of the calories, but there are some things that remain constant. We have the same number of Kleibert's law, we have the same number of heartbeats in our lifetime as an elephant does. We have the same number as a mouse. We have the same blood pressure as a blue whale. All mammals have these constant things that they share. And the thing that changes is metabolic rate. What does that mean? Well, in effect, it means elephants age much more slowly than we do and mice do. Elephants age so slowly, they don't get cancer. Their cells don't have enough time, well, they don't change enough, mutate enough to get the mutations that would cause cancer because they age so slowly. Whereas mice age really, really fast and die after like 6 months or something. Right? Elephants live a long time, as do blue whales. There are other of these interesting straight lines you find in graphs. So this is the summary. Metabolic rates in mammals follow this scaling law. But you also get this same thing happening with another type of complex adaptive system, which is organizations, companies, also have scaling laws that apply. So this is revenue from NASDAQ. I got it, this is back in some time ago, 2009. But what this shows is you double the size of a company, you don't generally double the revenue that you get out. Most, in fact, pretty much all listed companies, you only get between 75 and 85% of the revenue out. If you don't double the revenue, you get about 75, 85% of it that you'd expect. Which is different to Amazon, right? I showed you that graph of Amazon. They're in advance of that. They're going faster than this. So revenue scales with number of employees following the scaling law with an exponent of about 85%. So as a company doubles in size, unlike Amazon, you don't double the revenue. You don't more than double the revenue. Cities. I was in the Netherlands talking about this, and cities are the same. As you double the size of a city, you also get these interesting scaling laws applying. So as you double the size of a city, you don't have to spend double on infrastructure. So you'd expect, from going from one size to double, you'd expect double the amount of roads, right? Or double the number of lampposts, double the number of petrol stations. But you don't get that. You get about 85%. So for road length, for all these infrastructure things, you get this scaling law as you double the size of a thing. So for cities, for organizations, and for mammals, when you start to look at how size increase affects things, as you go from more simple, if you like, to more complex, or to smaller to bigger, you get these scaling laws applying. Geoffrey West, in the brilliant book Scale, I recommend this, it's in the bibliography at the end of the talk, and obviously the slides will be available. He says, quantities that do not change when other parameters of the system change play a special role in science. In other words, when you see straight lines on graphs, something's going on. You should go and have a look at it. Try and work out why. And that's what the Santa Fe Institute is there for. The Santa Fe Institute is there to try and understand why these things are happening and what the cause of them are. And that's really what the rest of the talk is. What I've been describing is what economists call economies of scale. So as you double the size of one thing, if the other quantity doubles, that's called linear scaling. If you get less, that's called sublinear scaling. So as X doubles, Y increases by less than double. This is what our chief financial officers say. We're going to double the size of our office, economies of scale, it'll be fine. And they're right, because as you double the size of an office, you need 85% of the network cables that you'd expect, or the telephone lines. These things do exist, economies of scale. So back to the Santa Fe Institute. Murray Gell-Mann wrote this book, The Quark and the Jaguar. He's trying to understand, as I say, why we get something as complex as us from a group of cells, or even subatomic particles. If you took me and put me in a blender, right, or any of you, put you in a blender, whizzed you all up, and you got like me soup out, and you poured me soup into a me-shaped mold, it wouldn't start talking again, right? It's not going to happen, right? we are more than the sum of our parts, right? We get this complexity arises from the simplicity of these small things. Murray Gell-Mann wrote this book because he was fascinated by it. So what are complex adaptive systems? So the definition of a CAS is they consist of self-similar components. So a mouse and an elephant, fundamentally they've got the same cells, right? The same size thing at the bottom of them, the cells. They are self-organized. There is no conductor. There's no organizing designer telling the elephant to organize into an elephant from a fetus. It just happens that way. They're complex, by which I mean the behavior of the whole is greater than the sum of the parts. You don't get me out of the blended James, right? That's something, it's impossible. I'm a more complex thing than that. And then you get emergent behavior. So you get, every time you run, if you have an experiment and you run it once, you run it again, you can't expect the same thing to happen, if you like, emergent behavior. So these are the four sort of properties that define complex adaptive systems. And those straight lines, further to that, can be described or can be predicted mathematically by three further simple principles. The first is the idea of a space-filling fractal network. Now, this is a hierarchical one. So you can think of this in your company as all the people you need to talk to get something done, right? The hierarchy of decision-making, of information flow through your company. In our bodies, it's our circulatory system or our nervous system. And in cities, it's water pipes, it's electricity cables. Hierarchical fractal networks. The second thing you need is invariant terminating units. So in mammals, that's cells. In companies or in cities, that's people and houses, essentially. Or people in cities and houses. Sorry, the other way around. I also think that this is a much better name for consultants as well, is invariant terminating units. We've been trying to get our HR people to call us that, but no, meat bags is what they insist on, so that's what we'll stick with. And the final thing you need mathematically to predict these straight lines is optimization. So a system that optimizes itself over time. So, geological time and evolution in terms of biological systems and market forces in terms of cities and companies. And just these three simple properties, mathematically, there are mathematical proofs, the papers at the end of this, will predict these lines, these weird straight lines, these weird scaling laws that we see in nature. The other thing is they're everywhere, right? Everything you look at, more or less, is a complex adaptive system, right? Us, the teams we work in, the companies we work in, the software we're building, the software architectures we sit in, these are all complex adaptive systems. And all of these things can be described, again, with these principles. And this is the key thing. All the examples I gave you are hierarchical network-based. And anytime you see a hierarchy in nature, you end up with scaling laws that follow the same principle, which is as you double one thing, you don't get double the other thing out. When you have a hierarchy, you always have sublinear scaling. It's maths, fundamentally. You can't get anything else. All right? So when you have hierarchies in your company, you're going to get that straight line that says you're not going to earn as much revenue as you might like. And it's down to the hierarchy itself. That property of your company causes the effect of sublinear growth in revenue. And then finally, basically, the self-similarity, we are the same as a mouse. We are the same as a blue whale, which is kind of a fun thing to think about, just of a Wednesday morning. Which brings me to what I was talking about with flow and value streams and building software to improve flow. There's a fun thing about corporate metabolism. Companies slow down as they get older. We slow down as we get older. Right? We age. So do companies. Right? Mammals age, companies age, cities age actually as well. So why does revenue growth slow as size increase? Right? We have this graph of revenue growth versus size. Why is it that metabolic rates slow? And it's interesting because it's literally down to the mathematics of the hierarchical network. The fact that you're going from a big thing in us, you've got a heart, that splits into arteries, splits into further arteries, and eventually has to turn into capillaries to feed our cells with energy. The depth of the hierarchy Just the depth of the hierarchy predicts where you are on that graph. An elephant's circulatory system is really, really deep. It's really slow metabolism. The Etruscan shrew, which it's about that size, my thumbnail rather, smallest mammal, it's got one layer or two layers of arteries, essentially, before it hits capillaries. The only thing different between the two of them is the depth of their circulatory system, the hierarchy. So the two things are pretty much the same. You've got the same invariant terminating units, you've got different depth of hierarchical network. And just those two things with feedback predict lower metabolic rates. So bigger animals are more efficient, right? Essentially, they don't have to take on as much calories, they don't have to burn as much energy to get the same thing done. And this is down to this hierarchical effect in the circulatory system driven by feedback. And it's true for companies too. As you double the size of a company, they are more efficient. They don't have to spend as much on infrastructure. They don't have to spend as much on desks and all that kind of stuff. But they also, as companies age, they tend to develop deeper and deeper hierarchies. As a mammal grows, an elephant will go from a small elephant and it will develop deeper and deeper hierarchies. And that effect slows down the metabolism. And it's the same thing that happens in companies. As you add hierarchy, things slow down. It's just maths. And in companies, it's based on market forces. They both slow down as they age. Which brings me back to flow. So I showed you this value stream map earlier. If you think about value stream maps, essentially they are a line through the corporate information flow of your organization. They're a line that goes from a requirement or a widget or a thing through to production, through to someone saying thank you to you. There are one route, if you like, through this network, through the hierarchy, that value stream map. And the thing is, the interesting thing about our circulatory system, one interesting thing, there's lots of interesting things, but one interesting thing is as an artery splits, evolution has optimized the cross-sectional area of the thing it splits into to be the same total as the thing it split from. Because if you didn't, you'd have turbulent flow at the boundary, and you'd get back pressure up the artery, putting back pressure on your heart, leading to heart attacks. This is why plaque in your arteries, cholesterol is bad, right? Because it stops it increases turbulent flow, adds back pressure up the hierarchy, up to your heart. You can see the same thing with messaging systems, right? When you've got a consumer of messages that can't keep up with the producers of the messages, you get this backup of events or backup of messages in your messaging queue. It's the same thing that's happening in our circulatory system. And it's the same thing that's happening in companies with these big hierarchies. When we look at things like queues, if you were to make all the work in your company visible, right? If you were to sort of print out all the JIRA tickets, right, all the stuff that you need to get databases built from ops, etc., and started piling them up in front of people who were doing that work or in front of the teams, you'd find these big, big piles of tickets everywhere, right, making the work visible. And that's what we see when we look at value streams. We see these queues of invisible information. But what those queues represent is plaque on our corporate arteries, right? They basically, it's the same thing as plaque buildup in us. It's plaque buildup in the information flow, the value flow in companies. And the more hierarchy you add, the more queues you add, and the more heart attacks you're effectively giving the organization you work in. Which brings you to another really important book, this book, Principles of Product Development Flow. If you haven't looked at this, it blew my mind the second time I read it. I think I was at the right time in my career. But it's all about the economics of queuing and queuing theory in what we do, and why queues in organizations are bad. Then we have, back to this idea of corporate metabolism. As companies scale, as they get older, as they get bigger, typically they add hierarchy. Most organizations can't see a way of scaling without developing deeper hierarchies, right? And because of that, things get slower. As we add these queues in, as we add piles of stuff, inboxes and outboxes in front of people, things get slower. As more work happens, and those queues get deeper, things get slower. But we also deliberately block our corporate arteries. Now, again, who's got a change request board in their organization? Or an architecture review board? No one's admitting it. You're all hipsters, aren't you? You're all in like really cool like scaling startups or something. Well, a fun fact from Accelerate, right? In Accelerate, research from Accelerate over the years, the State of DevOps reports, they point to the fact that change request boards are predictors of low organizational performance. Not correlated with, predict. If you have change request boards, architecture review boards, it predicts you'll be in the lower quartile, essentially, of performance in terms of revenue or in terms of whatever it is you're measuring yourself on. And that kind of makes sense, given what I was saying. Every time you put a stage in where you have to wait for 30 days for a decision, it's kind of like your heart having to blocking, your heart's like pumping behind, building up a load of stuff, and then after 30 days, you're kind of, phew, and all the, you're starving everything downstream of the stuff it needs to get stuff done. Predicts organizational performance. Which brings me to this point. You can monitor organizational health. You can use things like mean time to recovery, cycle time, change failure rates, and the number of deploys per unit time from the Accelerate, from the 4 key metrics, there's 5 now, there's resilience as well. You can use these in the same way that a doctor would monitor your blood pressure or your heart rate or your temperature, right? They're leading indicators of whether you might get sick or not. They don't tell you what you're sick of or what's going to happen, but they'll tell you if you're on your way to becoming sick, maybe. And we can use these in our own organizations to do the same. So, these 4 key metrics are leading indicators of organizational health, like monitoring heart rate and blood pressure. But the key thing is, improvement in those 4 key metrics, doesn't matter how hard you work, you're only be able to improve up to the limit imposed by the hierarchy the organization is imposing on you. You can't get better than the hierarchy. It's just maths. This is the last sad bit, organizational mortality. It turns out organizations die all the time, companies die. The half-life of a company on the exchanges is about 10.5 years, right? 50% churn on the exchanges every 10.5 years or so. Why is that? Well, it seems that the data points to the fact that as we grow as an organization, we forget what we did to start with that made us all the money, that made us successful. We stop spending money on R&D. We stop creating new products. We stop investing so much in that. Right? In the same way that as we get older, we have to spend more and more of our energy on maintaining our body, maintaining our aging cells. So do organizations. They spend more and more money on maintaining the organization itself rather than on developing new products and bringing new products to market. And they add more and more processes and constraints. You're a 100-year-old company, you're going to have a ton of processes and constraints. Do you remember 3 years ago when that thing happened, we deployed into production and everything went down on Black Friday? Right, now we've got an 8-week regression test that everything has to go through, right? We're going to add more and more stuff the older we get. And hierarchies grow and grow, because most organizations can't see a way of growing without adding hierarchy in. So, to sum up, you do get some benefits. You gain economies of scale for infrastructure if you are a hierarchical company. But you're only ever going to achieve sublinear growth in revenue. And finally, hierarchies imply mortality. Eventually, the company is going to die. It's going to be taken over. It's going to go bankrupt or whatever. So, now that I've depressed out of you, let me explain why Amazon are able to do what Amazon are able to do, and why some other companies do as well. So there's another type of scaling law, which is called returns to scale. You've got economies of scale, then you have returns to scale. What returns to scale means is that as you double the size of one thing, you get more out than you should. Super exponential growth. As X doubles, Y increases by more than double, as opposed to economies of scale. And cities, they have both types of scaling going on. They have economies of scale for infrastructure, and they have returns to scale for socioeconomic factors. So the amount of innovation, wage growth, the number of lawyers per city. You get more than double the number of lawyers as you double the size of a city. That's weird, isn't it? But it's true. Or software developers, wage growth, patents, all these things. But also downside, disease, pollution, crime. Socioeconomic factors scale with returns to scale. Superlinear growth. Whereas the other side of things, infrastructure scales sublinearly, road length, etc. Oh, and by the way, if you ever thought people walk faster in a bigger city, it's true. Actually true. MIT, they took a bunch of mobile phone data, events from mobile phones and stuff, and they actually worked out that, yeah, people do move faster as you double this, up to how fast your legs go. Obviously, in this city, up to the limit of how fast your little scooter things go, which I keep being run over by. And the reason is because social networks, right, are the things that drive this growth in cities. There's a different type of network. I talked about hierarchical networks, but you're all probably familiar with the idea of small world networks. Right? Small world networks, social networks. The network that exists between you and your friends, between the people on your team, the communications that exist between groups of people who know each other. And this is related to this idea of something called Dunbar's number, which was mentioned at the start in relation to how Amazon scale. Dunbar's number is not a single number, it's a range of numbers. And it's related to how we evolved from caves, from small groups of hunter-gatherers, a nuclear family of 5 or 6 people, through to then your tribe, which is going to be sort of 15 or 50. And these still, our brains are still hardwired via evolution to think in terms of this number of connections that we hold. So as cities scale, they scale by social networks, by social interactions. I get to choose to come here today, as you did, right? If you're in a village, Devoxx doesn't happen in a village, right? Devoxx happens in this city because it's big, because it supports a bunch of people who come together because they want to, they choose to learn, to drive innovation. And so the two types of networks lead mathematically to the two different types of growth. Hierarchies lead to sublinear, social networks lead to small world fractal networks lead to superlinear growth. What does this have to do with how we build teams and team topologies? Team topologies is a vocabulary to allow us to build our companies around social networks. Build these small teams that are independent, that are decoupled from one another, that are cohesive, built around Dunbar's number, right? And then grouped, scaled by Dunbar's number. Right, scaled by this idea of small world network growth, plonking little teams next to each other on the side as opposed to deepening hierarchies. Let's add another 50 developers to the 200 developers we've already got in our software development department. And the reason is because small world network growth, you just add bits on the side. Cities add suburbs. You can actually tell the health of a city by measuring what's called its fractal dimension, how crinkly the outline of the city is, tells you how healthy a city is. Detroit, in the 80s, its fractal dimension dipped. Now it's picking up again in the US. And it's because with fractal network, with these small world networks, you put stuff on the side, right? You don't have to insert stuff into the hierarchy. And so you can grow as a city, and if you're lucky as an organization that's chosen to grow this way, you can grow the same way by building more decoupled teams, by identifying parts of your business which you can isolate and scale around. So as cities grow, they gain economies of scale for infrastructure. They rarely die. You get 115% of the stuff for 85% of the cost. Are there any companies out there doing this? Well, I would argue that ThoughtWorks does, but this isn't a sales talk, so I'm not going to talk about ThoughtWorks. But we scale via Dunbar's number. We open offices. When we get to about 200, we'll open another office somewhere, right? Spotify. I think the Spotify model is basically like an attempt to write down, and I know we can do the whole Spotify don't work like that, whatever. It's an attempt to write down how you scale with the minimum amount of hierarchy using these squads that are building isolated parts of a product, right? And then combined into tribes and chapters and so on. Valve, now when they leaked their employee handbook, this was in it. It was leaked. It's basically them saying to their employees, this is how we grow, because this is what allows us to go faster, get more products to market more quickly. We're going to build stuff in isolation from one another rather than in hierarchies. Finally, back to Amazon and this number, 1.15. Now, admittedly, there's not much data. That was all that was available when I was putting the talk together. But that's the same number as the superlinear returns to scale number that you get from social network-driven growth. The fact that with Amazon, with AWS in particular, they're hiring teams, and they don't often have much to do with one another. I mean, if you've ever used any of the AWS APIs, that's the downside of it, right? Because every API is different. You never know which API, if one API is going to look the same as another one. But they've said that's okay, because that's a trade-off we'll make in order to be able to spin up and build new products as fast as we can. So as most companies get bigger, it gets harder to get bigger. But as Amazon gets bigger, it's easier for them to get bigger. And it's based on these ideas from team topologies, these value stream aligned teams, direct line of sight to a customer. It's based on architectures that are aligned to flow, aligned to the flow of value. And it's based on teams that are decoupled and cohesive. So I recommend going and taking a look at this. I recommend maybe thinking about how some of these team structures relate to how you're working. And maybe we can use this, again, as a ubiquitous language to be able to talk more effectively about organizational design for software delivery and for other things. So to summarize, I said right at the start that this was like my 30-year journey or whatever it is. I'm 47, I started programming when I was 9. This is where I've come to, right? This set of characteristics of microservices, and then fundamentally these 3 simple principles around how to optimize software development, software architecture, and our organizations to improve flow. And it's based on team topology, it's based on Accelerate, based on a bunch of other stuff. And finally, this idea of social networks. They imply super exponential growth. Hierarchies slow metabolic rate. Essentially, can we use team shapes that optimize for flow and use forcing functions to improve flow? This is the set of research that I used to put this talk together. Thank you so much for coming. I hope it was all right and you enjoyed yourself and enjoy the rest of the conference.